In this video, we're going to walk through the calculation of the Black-Scholes option pricing model by hand. And so in this hypothetical example, we're going to use Tesla and assume that they have an earnings announcement coming out shortly. Again, this is hypothetical. I haven't done any research on Tesla for this example, but we think that the earnings are very unpredictable. We don't know if they're going to be better than expected or worse than expected. So we don't know if the stock's likely to go up dramatically on better than expected earnings or go down dramatically on worse than expected earnings. All we know is that it's going to be very volatile, probably more volatile than the markets anticipate. And since we don't know whether it's going to go up, where we'd buy a call, or whether it's going to go down, in which case we'd buy a put, we just think options are undervalued. So we want to buy both a call and a put with the same strike price, same expiration, and we think both of these options are undervalued. So we're going to buy a February 465 call option and a February 465 put option. These options expire at the third Friday in February. That's 45 days from the time that I created this example. And we anticipate that the appropriate volatility to use in our analysis is 54%. Note that 54% represents the annualized volatility over the next 45 days. The current risk-free rate of interest is 1.5%, and the current stock price is $469. Note that I took a lot of these values from January 7th, 2020 when I made this example. The internet, these videos are around for a long time, so it might be 2025 and these prices might look absolutely ridiculous. Doesn't matter, this is just an example of how to go through the calculations. So quick summary of our inputs. The stock price is $469. The strike price, our exercise price, is $465. Our risk-free rate is 1.5%. There are 45 days remaining, and the volatility is 54%. These are the 5 inputs into the Black-Scholes option pricing model. So now we're going to calculate the value of the call and the value of the put using the Black-Scholes option pricing model, and we're going to do this by hand. So let's go through our example. Let's start with the Black-Scholes option pricing model. Black-Scholes option pricing model is pretty complex if you're not a mathematical person. The value of the call is equal to the current price times the cumulative area under the normal distribution at D1 minus, and this here is just the present value of the exercise price using continuous compounding, times the cumulative area under the standard normal distribution at point D2. In order to start this calculation, we have to start first by calculating D1 and D2. So the formula for D1 is the natural log of the price over the exercise price plus the risk-free rate plus 0.5 times the variance times time. Time is expressed in years, so it's not the number of days, it's the fraction of the year. All of that is over the standard deviation times the square root of time. Once we get that, then we'll calculate D2. That's a lot easier. Then we'll look up under the standard normal distribution table and be able to do the value of the call calculation. Once we get the value of the call, then we can use this formula to calculate the value of the put, which is based on the value of the call plus the present value of the exercise price minus the current stock price. So let's start with D1. With D1, we want the natural log of the price over the exercise or strike price. So let's go here. D1 is equal to the natural log of the price, $469, divided by the exercise price, $465, plus, back over here, the quantity risk-free rate plus 0.5 times variance So the risk-free rate is 0.015%. Express that in decimal. Don't put it in as 1.5, put it in as 0.015 plus 0.5 times standard deviation squared, or variance. So that's 54 raised to the second power. And all that is times time. Now remember, time is a fraction of a year, so there are 45 days remaining. That 45 days is going to be expressed out of 365. So 45 divided by 365. Now, one thing I want to address is a lot of times I'll have students ask, well, why don't we focus on trading days instead of actual number of days? And the answer is, for the most part, unless you're dealing with 1 or 2 days to expiration, it's not going to matter because we're looking at a fraction of a year. So if I use trading days, I wouldn't divide by 365, I'd divide by the number of trading days per year, which is normally around 251, 252 years, depending on the year and how the calendar breaks down and things like that. So the fraction is not going to change dramatically. Also, we have several approximations here. The variance, we're kind of guessing at that 54%. The error from using days over 365 versus trading days over trading days per year is not going to create a substantial difference. So we have all that. Now I'm going to put that in brackets to remind us that we're going to do that calculation first. And then once we've done that, we'll divide that by the standard deviation times the square root of time. So our standard deviation, I do need to go back here. This is not 54, it's 0.54. So just like we express the risk-free rate as a decimal, we have to express the variance as a decimal in order to be consistent. So going back to my formula now, I put in variance 54 times the square root of time. Time again is 45 over 365, and I can raise that to the 1/2 power, which is effectively the square root. So now let me go through this calculation. D1, natural log of 469 over 465 is 0.008565. If you wanted to, you could carry that out to more decimal places. We've probably got enough here. Now I want to go to this next section here. This is within parentheses. So I'm going to start with the 0.54 squared, multiply that by 0.5, add in 0.015, and that gives me 0.1608. And then I'm going to multiply that by the square root of time. 45 divided by 365, or not the square root of time, but time is 0.12329. Close the brackets and then divide by, I missed a parenthesis there, divide by 0.54 times the square root of time. I start with the square root of time here. So 45 divided by 365, take the square root of that, times 0.54, and that's going to give me 0.18961. I would encourage you to make sure that you're doing these calculations, you're coming up with the same answers. It's very easy when you're doing this by hand to make a math error, even if you have the setup right. So double check my calculations, make sure you're doing these correctly. Keep going through the math. D1 equals 0.1608 times 0.12329 plus 0.008565 gives me 0.02839 divided by 0.18961. And that's going to give me a value of 0.1497. Okay, that's my D1. Now, I don't actually want D1. What I want is the area under the cumulative standard normal distribution up to point D1. So here is a standard normal distribution table. My D1 is approximately 0.15. So I want to find that on my normal distribution table. Here is the 0.15. The cumulative area under that is 0.5596. Oops. So ND1 is equal to 0.5596. Next, I need to get D2. D2 is equal to D1, which is 0.1497, minus, just to recap, minus the standard deviation times the square root of time. Standard deviation is 0.54, and again the square root of time is 45 divided by 365 raised to the 0.5 power. So D2 is equal to 0.1497 minus 0.1896, and we did that calculation before, so you can save a step there. That equals 1497 minus 0.1896 gives us negative 0.0399. So again, I don't want D2, I want the area under the normal distribution table up to D2. And D2 is approximately negative 0.04. So I go up here and find that is 0.4840. So now I have my ND1 and ND2. Now I can calculate the value of the call. The value of the call is equal to the stock price, $469, times ND1. And just to recap, that's coming from this formula right here. Minus the present value of the exercise price with continuous compounding. And so that is the strike price divided by E to the risk-free rate times time. So let me just go over here and calculate that. Risk-free rate is 0.015. Time is fraction of the year again. It should be 365, not 465. Gives me 0.01849 and so on. And then what we do is just hit the E to the X key on your calculator. All calculators should have one of those. It's an exponential function. And when we hit E to the X for that, we're going to have 1.00185 and some other change beyond that. Now what I like to do, just to avoid some rounding error, is I put that in my memory key and then take the strike price, that $465, times or divided by this value here. And what that's going to give me is $464.14. So that is my present value of the strike price. Now note, that uses continuous compounding. If you'd like to use your financial calculator to do that, just set up your periods per year to 365. That you're effectively using daily compounding, and discount it for 45 days, you're going to get the exact same answer. So continuous compounding or daily compounding, they're close enough that it's not going to change the results. I multiply that by our ND2. Again, just flashing back to this formula here. So that is 0.4840. That's going to give me 469 times 0.5596, $262.45 minus 464.14 times 0.4840, 224.64, and the value of the call then is $37.81. Now I can solve for the value of the put. The value of the put, remember, starts with the value of the call plus the present value of the exercise price minus the stock price. Fortunately, we've done all these calculations, so we know the value of the call is $37.81. We add in the present value of the strike price, that's $464.14. And then we subtract the stock price, that's $469. That's going to give us a value of $32.95. Now this makes a little bit of sense because we can see that the call option is actually in the money. It's got $4 of intrinsic value. The put option is out of the money. So we should expect the call price to be higher than the put price, and that is the case. So that is the value of the call and the value of the put. Now, if we're buying the straddle, remember, we're buying contracts, so it's 100 call options and 100 put options for one contract of each. So that's going to be 37.81 plus 32.95. That's going to give us a total cost of $7,076 to buy that straddle. Okay, now there are some other questions. What are our break-even points? Well, note that we can't generate a profit on both the call and the put. When we're talking about break-even points, we're talking about break-even at expiration. And so what we're saying is we need to make $70.76 from the call, or we need to make $70.76 from the put. We're not going to make money off of both of those. So our break-even points based on the call, our call price is going to be able to be exercised at $465. So it needs to go up by $70.76 in order for us to make a profit on this. Which means the stock price is going to have to hit $535.76 in order for that to work. Alternatively, we can make our money on the put if Tesla falls far enough. So the break even based on the put is 465 minus $70.76. And that gives us $394.24. So our break-even points are $535.76 and up, are $394.24 and below. In between those price points, we're going to lose money. Once we get beyond those price points, we're going to make money on this. What is our worst case scenario? This is what a lot of people will get wrong. They're saying, well, you're buying a call and you're buying a put, so the worst case is the stock price doesn't move. But technically that's not true because our call is currently in the money. So worst case scenario would be our price drops to 465. In that case, both the put's going to expire worthless and the call's going to expire worthless, and we're going to lose our entire initial investment of $7,076. Now, obviously, that's going to be very rare, but that is the worst case scenario. So our worst case scenario is to lose $7,076, and that is going to occur when the stock price hits $465 at expiration. Lastly, assume you look up the option values online and find that the current price of the call is 33 and the price of the put is 28.50. Based on our valuation analysis, those options are undervalued, so we would definitely want to purchase this straddle. So those options indicate the option prices are undervalued and we would want to purchase the straddle. What if the current price of the call was, say, $43 and the current price of the put was $38? In that case, based on our analysis, the options were too expensive in order to either want to avoid the trade entirely, or we could sell the straddle and basically sell the call and the put, take the money up front, and then hope that the price doesn't swing enough that we lose money from the call to offset our entire amount that we received, or lose enough money on the put to offset the entire amount we received. So that walks through an application of the Black-Scholes option pricing model by hand. Thank you.